In today's lecture, we will be discussing the antiderivative of certain function. Let us begin by considering the derivative of the power function x raised to the power of n. So this is given by n times x raised to the power of n minus 1. Now using the same formula, if we apply the power rule to x raised to the power of n plus 1 divided by n plus 1, where n is a constant, then this will be equals to x raised to the power of n. So you can check that out. Now, what we have done is we have taken the derivative of a particular function, and this is giving us x raised to the power of n. Now, if we take the antiderivative of this function, the antiderivative of this function will be simply the function, and this will be equals to taking the integration of x raised to the power of n dx. And we have a constant that needs to be added. The importance of this constant will come much later. Similarly, we know if we consider our trigonometric function, we have derivative with respect to x of our sine function. So that gives us the cosine function. So that means if we take the antiderivative of this, then we should get sine x plus c, and this will be equals to taking the integration of cosine x with respect to x. So this is the formula for the integration of cosine of x dx, sine x plus c. Then we have derivative with respect to x of cosine of x. So this is equals to negative sine x. So what we can do, we can take this negative from the right hand side to the left hand side. So that means if we take the antiderivative of this particular function, then we will have negative cosine x plus the constant of integration c equals to integration sine x dx. So that means integration of the sine function gives us the cosine function, but that will be a negative cosine function plus the constant of integration c. So what we are observing here, that in order to obtain the antiderivative of a given function, we have to do is remember its corresponding derivative. So let's say we have derivative with respect to x of our exponential function. So this gives us the exponential function. So if we take the antiderivative, so that will be the exponential function plus the constant of integration c, and this will be e raised to the power of x dx. We can consider some other known function. We know derivative with respect to x of the logarithmic function, so that's 1 over x. So that means if we take the antiderivative, so this will be natural log of x plus c, which will be equals to taking the integration of 1 over x with respect to x. We can also use the inverse trigonometric function. So we remember that derivative with respect to x of the inverse tangent function, so that is 1 over 1 plus x squared. So that means if we take the antiderivative, we should get inverse tangent of x plus the constant of integration c. So this is equivalent to taking the integration of 1 over 1 plus x squared with respect to x. So this is the integration of dx over 1 plus x squared, which gives us inverse tangent of x plus c. So you can always pull out these formulas from the table of integral. So using this idea, let's try to perform some integration, and in today's section we'll be considering a method known as the method of substitution. So here we have to integrate the function 3x over 6x squared plus 4 with respect to x. So we need to do a substitution here. So we will be substituting the denominator 6x squared plus 4 with a new variable, let's call it u. Once we have done this substitution, we're going to take the derivative with respect to x on both sides. So this will be equals to du over dx. Now let's take the derivative of the individual terms. So derivative of 6x squared will be 12x plus derivative of 4 with respect to x, so 4 being a constant, this will be 0. So this is equals to du dx. If we take the cross multiplication, so we have 12x dx, this will be equals to du. or x dx will be simply equals to 1 over 12 du. So that means our integral, which is given by 3x divided by 6x squared plus 4 dx, so that will now become, in the numerator we have 3 times, we have x times dx, so x dx can be substituted with 1 over 12 du whole divided by, we have 6x squared plus 4, which we assumed to have the value u. So 3 over 12, this is a constant. So 1 over 4 will come out of the integral side. So we have du over u. Now we have to find out this integral. We talked about it. So we know that derivative of the natural log function gives us 1 over x. So here our variable is u. So that means derivative of the logarithmic function u, log of u, gives us 1 over u. So that means its entire derivative will be the integration of du over u. So we'll have natural log of u plus the constant of integration c. Finally, we have 1/4 times natural log of u, but u we assumed. So our value of u is 6x squared plus 4 plus c. So this is going to be the final value of our integration. So let us do another problem. So here we have to integrate the function x times e raised to the power of x squared. Even though this looks like an extremely complicated problem, but this is much more easier than you think. So we will use the method of substitution. So we will substitute the power of e, which is x squared, with, let's say, the new variable u. Now let's take the derivative on both sides. So we'll have 2x. We're taking the derivative with respect to x. So this will be du over dx. Now if we cross multiply and divide by 2, that will give us x dx equals to half du. Now we can see in our original integral, which is e raised to the power of x squared times x dx. So here we can rewrite it as e raised to the power of x squared. Also in place of x squared we have u, and in place of x dx we'll replace with it half du. Now half is a constant, so we can pull it out of the integral. So this will be half multiplied to e raised to the power of u du. So this is a very simple integral. So integration of the exponential function gives us the function itself plus the constant of integration. This is extremely important. This will be equals to half e raised to the power of u. So our u value is x squared. So we have half x squared plus c. So this is going to be our integral, the integration of the function x e raised to the power of e x squared with respect to x. Let's move on to the next problem. So here we have a function given by 1 over x times natural log of x. We need to integrate this function with respect to x. So let us begin. So we have to find integration of, so in place of fx we have 1 over x times natural log of x dx. We need to find its value. So we are going to make a substitution here. So if we take natural log of x equals to our variable, let's this time take y. We can choose any other variable other than x for our choice. To restrain yourself from taking the a, b and c, those are generally considered as constants. So if we now take the derivative on both sides with respect to x, the derivative of the logarithmic function will be 1 over x, and on the right hand side we have dy over dx. Let's cross multiply. So we have dx over x equals to dy. So we have to be a little bit careful while taking this substitution, because here when we take natural log of x equals to y, we have dx over x. So that means this integral can be, let's rewrite it as integral. So we have 1 over natural log of x. So this is multiplied to dx over x. Now things becomes more easier when we look in this particular fashion. So this is 1 over, so we have natural log of x, so this is simply y, and dx over x, so this becomes dy. Now this is a simple integral, integration of dy over y, so this is natural log of y plus the constant of integration c, and we have to replace the value y with natural log of x, so this will be log of natural log of x. We'll consider the absolute values as well, plus c. So this is the value of our integration fx dx. Let's move on to the next problem. So here we have a definite integral, because this time the limiting values are given. That means the value, we have to calculate the value of this integral at the endpoints 0 and 2. So this is actually x equals to 0 and x equals to 2. So let us begin. First, let's not talk about the endpoints. We will only consider indefinite integral, integration of 2x times integration x squared plus 5 dx. Now we are going to make a substitution. Here we can see that if we take x squared plus 5 equals to some variable, then taking its differentiation is going to give us 2x. So we'll do that substitution. So let's take x squared plus 5. We could have simply taken x squared, but then again, if we take the plus 5 as well, this is not going to be of much difference, but instead it will be simpler for us to perform the computation. And the reason behind this is plus 5 is a constant, because we'll be taking the derivative, so its presence will not be of much effect here. So let's this be equals to, let's say we take a variable t. We'll take the derivative both sides with respect to x. So this will be 2x, which will be equals to dt over dx. Now we'll take the cross multiplication. So with 2x dx equals to dt. So that means this integral now transforms to, so we have square root of x squared plus 5. So we'll replace it with t. So we have square root of t times now 2x dx. So this will be replaced with dt. This can be also written as t raised to the power of half dt. We'll be using the power rule. So the power rule for integration is simply t raised to the power of half plus 1 divided by half plus 1 plus the constant of integration c. So this is c. Now let's substitute the value of t with x squared plus 5. So we have x squared plus 5 whole raised to the power of, so we have half plus 1, which will be 3 over 2. And in the denominator, we also have 3 over 2. So we will simply write it as 2 over 3. We have plus c here, but the whole reason we're writing it plus c, because this is considered as a indefinite integral. The moment we calculate this function at the endpoints, then we do not have to mention this c. So the c is now calculated. So how to calculate this indefinite integral? This definite integral. So we'll use the function 2 over 3. We have x squared plus 5 raised to the power of 3 over 2. All we have to do is replace the value of x with the upper limit. So 2 squared is 4. So 4 plus 5 will be 9. So we have 9 raised to the power of 3 over 2 minus the same function 2 over 3. Now in place of x, we will replace it with 0. So we have 0 plus 5. So this is 5 raised to the power of 3 over 2. This value will be 18. So we have 18 minus 2/3 of 5 times 5 raised to the power of 3 over 2. So this is going to be our final value for this definite integral. Let's do one more problem. Let's obtain the value of this given integral. So we will consider x cubed to be equals to our variable u. Taking its derivative with respect to x gives us 3x squared equals to du over dx. If we cross multiply, we have 3x squared dx equals to du. So what we'll do this time, we'll do a change in variable as well. Change in variable. The meaning of this is this, because once we do the substitution, our integral then becomes, so in place of 3x squared dx, we have du. And secant squared x cubed, so this becomes secant squared u. So this is our integral. So what we've done, we have transformed our integral from the x variable to the u variable. So and the limits that we have, these are the limits for the endpoints x. So what we want to do is, we want to change it to the endpoints of u. We want to write it in terms of u. So that's very simple. We only have to consider our original substitution, x cubed is equals to u. So when we have x approaching 0, then in that case the value of u will be 0 cubed. So this is 0. So this value will be 0. And when x approaches the value pi over 4, then the value of u will be pi over 4 cubed. Now let's do one thing. This looks very complicated. Instead of pi over 4, let's consider pi over 4 whole raised to the power of 1/3. That means x is cube root of pi over 4. So if we take the cube root of pi over 4, so the cube root, the whole raised to the power of a cube, the cube root goes away. So we are left with u is equals to pi over 4. Right. This will become simpler to calculate. Although there's nothing wrong if we simply take pi over 4 for the value of u. So this is cube root of pi over 4. Right. Now this is a new integral. We know that integration of this particular value, that will come from the definition. Derivative with respect to f of the tangent function gives us the secant squared function. So that means integration of the secant squared function should give us tangent x. So this will be equals to tangent of u. Now we will use the limits from 0 to pi over. So let's take it. So we have tangent of pi over 4. We have substituted the value of u with the upper limit pi over 4 minus tangent of the lower limit, which is 0. Tangent of pi over 4, so that's 1, and tangent of 0 is 0. So this is going to be the final value of our integral.